We've covered why stoichiometry is not always reflected in the rate law of a reaction. And that happens due to the idea that there are elementary reactions that can form multiple steps in a single reaction. But why does the value of the rate constant change with things like temperature or pressure? Well, that comes down to this idea called collision theory. Collision theory is the idea that reactants aren't going to connect and form products unless they actually get close to each other and collide in the right way. We can look at a reaction in order to bring this idea forward. Let's think about a methyl cation reacting with a hydroxide anion to form methanol. Let's break out the good old ball and stick model to investigate it. I've got a methyl cation here. It's a carbon that only has 3 bonds made. It's desperate to make another bond. And then I have the hydroxide anion here. It too is desperate to make a bond. It's got an extra electron. It would love to be attracted to something. But if these two collide in the wrong way, in the wrong orientation, no reaction occurs. In order for these to get a reaction, they have to collide in the right orientation. And even then, if they don't react with enough force, with enough energy, this could hit and just break right apart. They have to connect with enough energy to stick, and then they'll actually form those products. So the whole idea behind collision theory is that my reactants need to have enough energy and the right orientation to connect and stick. Now that seems really unlikely that these two would connect at just that right orientation. And it is. But remember, when we have a lot of reactants, we don't just have 10, 20. We're not talking in the order of tens or hundreds of reactants when we have a lot of reactants. We're talking about moles of reactants at a time. Remember, a mole is 602 septillion molecules. That's 600 billion trillion molecules all colliding at colossal speeds. So when we say this is unlikely to happen between just 2 molecules, that's fine, because we're multiplying that unlikeliness by 602 septillion. So that still doesn't quite explain why the value of K is so dependent on that temperature. Well, we can look further at that by drawing out a Maxwell-Boltzmann diagram. A Maxwell-Boltzmann curve is a graph that represents the distribution of velocity and energy across molecules at a certain temperature. You see, our temperature reflects the motion of the molecules in our system. But not all molecules are going to be moving at the same velocity. So if I'm at, let's say, 80 degrees Celsius, the distribution of my molecules, the distribution of their velocities, could look something like this. But those same molecules at a higher temperature, let's say 200 degrees Celsius, could look more like this. And so I could have the same number of molecules, but when I get to a higher temperature, more of my molecules shift to the right. They have a higher energy level. So really, as I increase my temperature, I'm not just shifting this curve to the right. I'm flattening it down to the right. I'm increasing the ratio of molecules that have more energy. I'm not just giving everything more energy, I'm only giving some things more energy. And so because of that, if the amount of energy that's required for this kind of connection to occur, that could be somewhere right here. Let's say right there. That's my energy threshold. Below this energy, no reaction. Even if the molecules are perfectly aligned, there will be no reaction below that threshold. Above this threshold, I get a reaction. If I also have the proper alignment. So temperature and pressure are able to increase the rate of my reaction because I'm moving more molecules into this higher threshold. If there's more molecules above this threshold, then when these collisions do happen, they will stick. But this also shows why most reactions don't go to 100% completion, because I have all of these reactants here, all of these reactants, that in both cases just don't have enough energy to react. So if they hit, even if they collide with each other, they're still not going to react. I need my reactants to have the right amount of energy and the right alignment in order to connect. So that's why we can see that our value of our rate constant is very dependent on temperature. And by understanding collision theory, we can make sense of a lot of the fundamental ideas behind why our rate laws look the way that they do.